Every application, no matter how beautifully designed, relies on data. But when all that data lives on a single centralized database server, you're building on a fault line. Hardware fails, disks corrupt, power supplies die, and when that single server cracks, your entire system goes dark. Relying on one database node creates two simultaneous disasters when it fails. First, immediate downtime. Your application cannot process logins, transactions, or searches. Second, and far worse, you face permanent data loss if the storage drive itself is unrecoverable. Database replication solves this vulnerability. It operates as an active, ongoing mechanism that instantly copies data across multiple nodes, ensuring that a live replica is always ready to take over the load. Today, we are going to design a highly available architectural blueprint. We will walk through the exact configuration settings, topology choices, and failover mechanics required to keep your data intact when a crash happens. This approach accepts that we cannot prevent servers from crashing. Instead, it ensures we build a mapped cluster capable of surviving those inevitable hardware failures without your users ever noticing a disruption. Step 1 in our design is selecting the network topology. We need to determine the logical path data will travel between the primary and secondary nodes. This diagram shows a primary-based architecture. A single master node receives all incoming write operations, then streams those changes down to worker nodes handling read requests. This layout gives high read resiliency, making it ideal for systems with heavy query traffic. Now look at the diagram's right side, showing multi-master replication. This active-active setup allows multiple nodes to accept writes simultaneously. If your application is distributed across geographic regions and needs high write availability everywhere, this bidirectional layout is necessary. To build your own blueprint, you need to map out your primary and secondary nodes based directly on your application's traffic. If you are read-heavy, draw a master-slave tree. If you need writes anywhere, map a master-master mesh. The chosen layout dictates exactly how your system scales and where its physical failure boundaries lie. Now that we have the macro-level network mapped, we have to look at the microscopic level. Your topology is only as stable as the format used to encode all the data traveling across those network links. For many years, databases have used statement-based replication, sending the exact SQL command from the master to the target replica. But if you send a non-deterministic query, like an update using the now timestamp function, the replica might execute it a fraction of a second later than the master. Because the commands are executed slightly apart, those timestamps won't match. This causes silent, irreversible divergence. Your primary and replica databases now hold different data. To fix this, you must configure your system to use row-based replication. By setting your configuration parameter binlog format equals row, you stop sending raw SQL commands. Instead, you copy the exact physical blocks of modified data and perfectly drop them directly into all the replica nodes. Encoding physical row changes ensures that the resulting data is exactly the same on every node, guaranteeing absolute mathematical consistency across the cluster. With our data strictly formatted, we have to address how the nodes communicate. Under standard asynchronous replication, a master sends data out and immediately returns success to the client.
If that master crashes before the data reaches the replica, that in-transit data is gone forever. We solve this by upgrading our durability with semi-synchronous replication. This configuration forces the master to pause and wait for proof that the replica has completely safely received the data. But the timing of that pause is critical. If you set the wait point to after commit, the master commits the data locally to its own storage engine and then waits while the packet slowly travels toward the replica to be acknowledged. This creates a dangerous window. External clients can query the master and read that committed data while the replica is still waiting for the packet. If the master suddenly crashes in this exact moment, those external users are holding data that the surviving replica has never seen. This is called a phantom read. You must strictly configure your waitpoint variable to after sync. Watch how after sync changes the sequence. The master writes the log and sends it to the replica, but it blocks the local commit. Only after the replica mathematically acknowledges possession of the data does the master commit, allowing the users to see it. Shifting this wait point by a few milliseconds eliminates the phantom read vulnerability entirely. It is the absolute prerequisite for executing a lossless failover. We've secured the data transport, but we have a final architectural challenge. managing concurrent operations and the natural timing delays of a distributed network. In a master-master environment where any node can accept a write, two clients might attempt to update the exact same record at the exact same time. Left alone, these bidirectional writes will collide and corrupt the database. To mitigate this, multi-primary setups require a consensus protocol, like Paxos or an optimistic validation framework. This protocol acts as a strict referee, ordering the transactions globally and automatically dropping conflicting writes before they can commit. Master-slave environments have a different weakness. Because worker nodes are busy processing, they can fall slightly behind the master node. If a user writes to the master and immediately reads from a trailing replica, they will see stale, outdated information. You prevent this replication lag by implementing log sequence number, or LSN tracking, directly at your application routing layer. This mechanism tracks the exact replication position, ensuring the app only reads from a replica that has caught up to the user's latest write. By adding these conflict resolution and routing layers, you transform a collection of independent hardware into a single, cohesive, self-healing organism. Let's review our completed blueprint. We mapped the ideal topology for our traffic, locked our data format to row-based logging, enforced durability with the after-sync wait point, and implemented protocols to handle write conflicts and replication lag. You now possess a system engineered to survive a catastrophic failure. If a node burns down, the architecture handles the transition mathematically, ensuring you do not lose a single committed transaction. Your next step is to test this. Boot up this cluster design in a staging environment. Then cut power to the primary node and watch your failover strategy trigger instantly as the backup server takes the load. We cannot prevent hardware from breaking, but with rigorous replication design, we can render those breaks completely invisible to the world.